Hello. So today we will continue with our chapter on vibrations and waves. Okay, let's remember a few things from last week. So we learned that in a spring mass system, one there is no friction, the mass will be oscillating between plus x maximum and minus x maximum. Okay, and we learned that at x maximum, the velocity will be zero because the object will come to rest, and the acceleration will be a maximum, okay, because the tension will be maximum and the tension is related to the acceleration. So the acceleration will be maximum. Then on its way back, it will pass by the equilibrium position where x equals 0, v will be v maximum and a will be 0 because at equilibrium, there is no tension, that the spring will be relaxed, there is no tension, so there is no acceleration, okay? And then it will continue to compress the spring where x will be at minus x maximum. Again, the object will stop and the acceleration will be a maximum. And then it will repeat the same thing. Few vocabulary that we learned. The period of the oscillation, it's the time taken for one oscillation to finish, okay? So it's the time needed for one full cycle, okay? Frequency F, it is the number of oscillations per 1 second, okay? If we have the period, we just divide 1 over t and we get the frequency and the unit is hertz. The other way around can also happen. If we have the frequency and we want to get the t, we also say t equal 1 over f, okay? Then omega is angular frequency. It's another form of frequency. It is basically f times 2 pi. Now for mass spring system, omega is also square root of k over m, okay? It's also square root of k over m. We can write this equation as also as omega square equal k over m. So there is two ways to write this equation. Omega equals square root of k over m, or omega square is equal to k over m. X maximum is the amplitude. So if they ask you about the amplitude of the oscillation, I just look at what is the maximum value the mass reaches. Sorry. V maximum is omega times A, okay? And we learned in the lectures of last week how to do this derivation. You are not responsible for the derivation. You just have to memorize this formula. A maximum is omega square A. Okay. Now, graphical representation of position in simple harmonic motion, which is the motion of a mass spring system when there is no friction. If we look at it, we will find that the object will go from equilibrium, for example, in this case, from equilibrium to the maximum, to the equilibrium, to the minimum, to the back. Sorry, from the equilibrium to the maximum, to the equilibrium, to the minimum, back to the equilibrium, to the maximum, to the equilibrium, to the minimum, and this will keep repeating itself in the case of there is no friction, okay? Now, what information we get from the graph? From the graph, we get two pieces of information. We get the amplitude, which is the maximum value on the x-axis, and we get the period, which is peak to peak, or equilibrium to equilibrium, or valley to valley, okay? This will be the time for one complete cycle. Once we have the time, once we have the amplitude and the time for one complete cycle, we can derive f because it's just 1 over t. We can derive omega because it is 2 pi f. We can derive v maximum because it is omega times a. And we can get a maximum because it is omega square a. Also, now, just one thing I want you to pay attention to. If the object is at the maximum position or at equilibrium or at the minimum, I want you directly to know that the V value, what is the V value for it, okay, or the A value for it? Because at the maximum elongation, V will be 0, A will be A maximum. So you don't have to try to do any calculations. It is at the maximum position, so V equals 0, A equal A maximum. It is at equilibrium, so V equal V maximum, A equals 0. It is at the minimum compression, so V equals 0, A equal A maximum, okay? But what if the object is not at these three particular values. So what if it is not at x maximum, it is not at x0, it is not at x minus x maximum? What if it's at another value x as shown here in red? In this case, if we want to calculate like the V of it, we have to use conservation of mechanical energy. And we have the right to use it because friction is zero. We don't have any friction. So mechanical energy is conserved. So mechanical energy at x is basically mechanical energy at x equal the amplitude, okay, or x equal x maximum. Now, what's happening at, sorry, what's happening at x equal x equal any value of x? There is kinetic energy because it is moving, and there is EPE because it is the spring is either elongated or compressed. So there is two forms of energy at any value of x. And this is equal mechanical energy at x equal to A. What's the definition of kinetic energy? It's half mv squared. What's the definition of EPE? It's half kx squared. And what is EPE at x equal A? It is half KA squared. Now all the halves cancel out because it is a common denominator, okay? And I get the equation mv squared plus kx squared equal KA squared. Okay, so if they ask me the question, find V at a particular value of X, I come to this equation. You can do the derivation. It's so simple. You just say mechanical energy at X equal mechanical energy at X equal A, kinetic energy plus elastic potential energy equal elastic potential energy at A, half mv squared plus half kx squared equal half ka squared, which means mv squared plus kx squared equal ka squared. So if we want to get V at a particular X, I use this value. And I will get the A from the graph, for example. Or if they ask me to calculate X at a particular V, I also use this equation, okay? Let's do two exercises from your booklet. So this is exercise number 2, page 47. Okay, so as a block is attached to spring, oscillates on a frictionless, so there is no friction, horizontal surface. The block position as function of time is shown in the figure below. Okay, so this is X as a function of time. Okay, what is the position X0 of the oscillator at time equals 0? So what is happening at time equals 0? What is the position at time equals 0? The position, so part A, as you see, at time equals 0, X equals 0. So at time equals 0, X equals 0. We got this from the graph. Okay, part B. Find the amplitude of the oscillation. So where is the amplitude? It's the maximum value reached by X. So in this case, it is 6 what? 6 centimeters. So A is equal 6 centimeter. We never keep it in centimeter. We change it to meter, which means we divide by 100. So this is 0.06 meter. Okay. Again, this is graphically or from the graph. Part C, determine from the graph, determine from the graph the period of the oscillation. So we come to the period of the oscillation. How do we calculate it? We either take one full cycle. So first it was here, then it went down, then it reached back here, then it went up, then it came back here. Okay, so this is one complete cycle. Now, if we take another color and we start from here, it is here, it went down, then it is back here, then back to the maximum value, then back here. Okay, so this is one complete period. Now, how much is this one complete period? It's one what? It's 1 second. So the period, part C, equal 1 second. Is there another way to get the period? This graphically. Can we see the period in a different way? Yes. For example, we can look at the maximum to the maximum. Okay, so we can look at from the maximum to the maximum. How much is this value? This is 0.5. This is 1. So the middle is 0.75. And this is 1.5, and this is 2. So the middle is 1.75. So from 1.75 to 0.75, this is again 1 second. No matter where you take the initial and final position for the period, they will always give the same value. Now, part D, deduce the frequency. Once they tell me deduce, it means I have to use the information from the previous question. So I have the period in the previous part to be 1 second. So the frequency will be 1 over the period, which is 1 over 1, which gives me 1 hertz. Remember, the unit for frequency is hertz. And then I have to get omega. Omega is, here it is, 2 times pi times f, which is equal to 2 times 3.14 times 1, which happens to be 6.28 radian per second. Okay. Part E. Part E, find the position of the block at t equals 0.75. So I come to my graph. And I look what's happening at 0.75. So 0.75 is here in the middle. So this is t equals 0.75, and this is x. So how much is x at 0.75? At t equals 0.75 second, x equals 6 centimeter, which is 0.06 meter. Okay. Then we have to deduce its speed at that time. Okay. So here, this is a special position. This is the position where x is equal to a, okay, the amplitude. So what happens at the amplitude? What happens to the v? How much is v at the maximum elongation? Here I have to remember the thing that at x equal x maximum, v is equal to 0, okay? And we have just deduced it from the fact that x is equal to the amplitude, so v is equal to 0. Over here, I don't have to use conservation of mechanical energy because this is a specific position, which is x equal x maximum. The velocity is equal to 0. Another specific position is x equal is when x is at equilibrium. Okay, when x is at equilibrium, v is equal v maximum. Okay, at x equal, for example, here they asked me at t equal 0.25, what happens to x here is minus x maximum, so v is also 0. Now they asked me what is a at this value. A is a maximum. What is a at equilibrium? A is 0. And what is a at minimum? A is a maximum. Okay. Let's do another exercise. So a block of mass m attached to a spring of stiffness k equal 500 Newton per meter. It oscillates in simple harmonic motion. The oscillations are recorded as a function of time on the graph. Find the amplitude of motion. So this we just steal it from the graph. So the maximum is 0.1 what? Meter. So part A, amplitude is equal to 0.1 meter. Okay. Find the period and the frequency of oscillation. So for the period, I choose any two values I want to start with. The easiest I can see is from here to here, because you see this is one full cycle. It goes from equilibrium to the minimum, to the equilibrium, to the maximum, back to the equilibrium. Then it repeats itself, right? Then it repeats itself. So this is one complete cycle. The time for it is 0.1 seconds. So the period T is 0.1 seconds. Then deduce the frequency. So then the frequency is 1 over 0.1, and this gives me 10 hertz. Okay. Now calculate omega. So part C, calculate omega. Omega is equal to 2 times pi times f, which is 2 times 3.14 times f, which is 10. Okay, and this will give me 62 0.83 radian per second. Okay, then find the mass attached to the spring. So here we found omega, and now it's asking for m. Here I have to remember this formula. Omega is k over m, or which is the same as omega square equal k over m. Okay, so I use this equation. So I come here, I say omega square equal k over m. Omega square is 62.83 square equal k is given 500 over m. Cross multiplication, I will get m equal 500 divided by 62.83 square, and this is equal 0.126 kilogram. Okay. Okay. Part D. Part D. Calculate the position when the speed is equal to 5 meters per second. So they are giving me the speed. The speed is 5 meters per second, and they're asking me to calculate x. So here, what do I have to use? Here, I don't have any option but to use friction equal to 0 implies mechanical energy is conserved. So I have to remember that mechanical energy at V equal 5 meters per second. This is equal to mechanical energy at x equal a. So I always take the other side to be at x equal a, because I know that the mechanical energy there is half k a square, and I know the amplitude. Now, what is mechanical energy at v equal 5 meters per 5 meters per second? So it is kinetic energy at v equal 5 meters per second plus EPE at v equal 5 meters per second. This is equal to EPE at x equal to. Okay. Okay. Now, kinetic energy at v equal 5 meters per second is half m times v, which is, okay, v square, but what is v? It's 5, okay? And what is m? I calculated it in the previous part, so it is 0.126. And here we have half plus half k is 500 times x, my unknown. This is equal half times k, which is 500, times amplitude square. And I know how much is the amplitude. It's 0.1. So I just plug it. Okay. So now this is one equation we have to solve for x. We can get rid of all the halves because it's in the whole equation. So we can get rid of all the halves like this. Okay, and now we solve. So we have 0.126 times 5 square, which is 3.15, plus 500x equal 500 times 0.1 square is 5. So I get 500x equal 5 minus 3.15. So 500x is equal 1.875. So x should be x squared here, right? So this is EPE. This is x squared. Yeah. Okay, x squared, sorry. Okay, and now we get x squared equal to 1.875 divided by 500, which is equal to 3.7 times 10 power minus 3. I do square root for both sides or radical both sides, and this will give me 0.06 meter. Okay, so it's somewhere here. This is 0.05, so it's somewhere here, 0.06. Okay, it's somewhere here. So I hope you found this lecture beneficial. We tried to use the formulas again and again, the period, the frequency, the rate, the angular frequency, how to use conservation of mechanical energy to find the x or the v at a particular time, and how to determine what is the x or what is the v from a graph, if it is at equilibrium or it is at maximum compression or maximum elongation. Okay, so tomorrow we will continue with the same chapter, trying to solve more exercises. So that's it for today, and bye-bye.